students. Hi, I am Vipin Mishra and I welcome you all in this foundation series of power electronics. So this is the third lecture of power electronics. In the first lecture, we have discussed what power electronics is all about. In the second lecture, we have discussed how different switches are being realized as per the application in particular converter. Now in this lecture, we are going to cover the Fourier series and its use in power electronics. Now this is one point where I have seen most of the students are struggling. Whenever we are studying any converter, we have to write the Fourier series expression for the voltage and current waveform. And that's the point where I have seen most of the students are struggling. I have listened so many students saying that this part is very difficult for them, and to memorize these expression in order to solve the gate problem becomes an Herculean task. So just attend this lecture and you will feel that this is not at all very difficult, and from after this lecture it will become very easy for you. Now the question arises, why do we exactly need Fourier series in power electronics? So see, we have different types of converter in power electronics, whether it is rectifier, choppers or inverter. Now when these converters are operating, due to the switching actions of the switches, there are harmonics both at the source end and both at the load end. And this is the first case. Now if you want to know about the harmonics, you have to write the Fourier series expression, and then you will be able to recognize which frequency components are present in the output or input waveform wherever you are doing the Fourier analysis. So first of all, you have to recognize which frequency component is present, and Fourier series is the tool for doing exactly the same. In power electronics, you will realize that most of the waveform, they are periodic, but they are not sinusoidal. And most of the cases when you have to calculate the power, you need to express that particular non-sinusoidal but periodic waveform or quantity into the sinusoidal signal. And again, this is where the power electronics comes into play. So this is why we are using Fourier series in power electronics. Now why exactly we are doing so? So let me tell you first about Fourier series. So you know, Fourier series is used for periodic signals. So the ultimate condition is, first of all, the signal must have to be periodic. So let us consider a signal xt. So if x of t is periodic, so if x of t is periodic, that means x of t plus t is x of t, where t is the fundamental time period. We all know about that. So if the xt is periodic, then this signal xt can be expressed into its Fourier series expression x of t. This is equals to a naught plus summation n equals to 1 to infinite a n cos n omega naught t plus bn sin n omega naught t. So if the signal xt is periodic, we can express that particular signal into its multiple harmonic terms, isn't it? Now if we expand this expression will be like this: a naught plus, if we expand this will become a1 cos omega naught t plus a2 cos 2 omega naught t plus a3 cos 3 omega naught t, and similarly other cos components will be there. Similarly, the sine components will also be there: b1 sine omega naught t plus b2 sine omega naught t, 2 omega naught t. Similarly, b3 sine 3 omega naught t, and so on. So now can you see one thing? Omega naught is the fundamental frequency term. Omega naught is the fundamental frequency term. Omega naught is the fundamental frequency, and can you see in this expression we have components like 2 omega naught t, 3 omega naught t. Good evening, Nikhil. 2 omega naught t, 3 omega naught, like these components are also there. So these components, 2 omega naught, 3 omega naught, and so on, these are the multiple frequency terms. These are the multiple frequency terms, and these are normally called as the harmonic as with respect to the fundamental term, okay, and we have one constant term as well. So A naught, this is constant term or this is DC term, okay. Okay. So what you can see here, if the xt signal is periodic, we can express that particular signal into its multiple harmonic terms, isn't it? I like your teaching approach and one of the best faculty of PE. Very good. Good evening, Nayan. Good evening, Nikhil. So, if the signal xt is periodic, what we have done here, we have expressed that particular signal xt into its multiple harmonic component. Now, it depends upon the signal which harmonic component it is carrying, isn't it? Where omega naught is the fundamental frequency terms and all the multiple frequency terms, they are normally referred to as the harmonics, okay. So, this is how Fourier series has expressed a particular signal into its multiple harmonic terms. Now, it depends upon the signal which harmonic terms it is carrying or it is not having a particular harmonic term, okay. Now, exactly why we are doing this analysis? See, let us suppose we have a waveform like this, a pure sinusoidal waveform, okay, having only multiple only fundamental frequency term, okay, having only the fundamental frequency term. Now, if suppose we have this kind of waveform which is having some harmonic component, now this waveform may have omega naught, 2 omega naught, 3 omega naught and so on component, depends upon the signal, okay. So, we have two cases in which we have a pure sine wave. This is the pure sine wave and this is a sine wave having the harmonic as well, okay. This is the sine wave having some harmonic component, distorted sine wave we have to say, okay. This is what? This is distorted wave. So, this is distorted wave. Now, let us suppose we have an induction motor application. Now, let us suppose we have an induction motor application. Now, if we give this particular signal, this pure sine wave to this induction motor, it is going to produce a uniform torque. It is going to produce a uniform torque and the motor will operate very smoothly, isn't it? Now, let us suppose we are giving this particular waveform with full of harmonics, okay. Distorted waveform we are giving to this induction motor, the uniform torque nature will not be there. It will produce a non-uniform torque right now. So, it is going to produce a non-uniform torque. The motor operation will become noisy. In some cases, it may even stall as well, okay. The thermal energy dissipation might be there. So many disadvantages will be there. So many disadvantages will be there just because of harmonics, okay. We will discuss about these phenomena as well in a particular lecture in which we will be discussing only about harmonics. But right now, these are required just to understand the concept of Fourier series in power electronics. So, we will be very restricted with this particular topic, okay. So, if you are giving a very pure sine wave to induction motor, it is going to produce a uniform torque. Let us suppose we are giving this distorted waveform having harmonics, then this same induction motor is going to produce non-uniform torque, noisy operation, it may even stall and thermal energy dissipation, everything will be there. Not at all best for us, okay. So, what do we need? We need to give this particular waveform, but if we are using power electronic converter, we might be having this particular waveform. So, if we have this particular waveform, we cannot use this particular waveform as it is. So, what we need to do? We need to remove these harmonics. So, what we do? We will give this particular waveform to filter and the filter is going to remove the harmonic component and then again we will recover back the pure sine wave. We will recover the pure sine wave. So, filter is going to remove the harmonic component. So, filter will remove the harmonic component and we will get back the pure sine wave again. But guys, first of all, filter has to remove which harmonic component? First of all, the filter has to recognize this particular thing. You have to design the filter as per the requirement. So, first of all, what you need to do? You need to do the Fourier analysis of this waveform. So after doing the Fourier analysis of this waveform, you will recognize that this waveform is having omega naught, 2 omega naught, 3 omega naught component, and you only require the omega naught component, not the others multiple frequency component. So you will use a filter that will remove 2 omega naught and 3 omega naught and so many components. It will only retain the fundamental component, and this is how you will get the fundamental waveform only, the pure sine wave only. So you have to recognize which frequency components are present in a particular signal, and for that you have to analyze the Fourier series of this particular waveform. See, if we are expanding a signal into its Fourier series, what we are getting? We are getting a knowledge which frequency component it is having and which frequency component is not present. So let us suppose that 2 omega naught, let us suppose that 3 omega naught, 5 omega naught, 7 omega naughts are missing, all even components are, let us suppose that odd components are there and even components are missing. So we will design our filter like that. It will remove all the odd component, it will retain only the fundamental component, and this is how we will filter the harmonics and get the pure sine wave again back. So for that we need to express the signal in terms of its harmonic component. In power electronic application, you will see very frequently, you will see that the waveforms that you are getting for different converter, they are periodic in nature, but they are not sinusoidal. Okay, and suppose you have to do some power analysis, you have to do some calculations like energy, RMS value and power, everything. So for that you have to express that particular waveform into its sinusoidal component. So who is doing this particular task for us? If you see, Fourier series is exactly serving its purpose. So if the signal is periodic, you can express that signal into its multiple harmonic component having sinusoidal nature. Is that clear? In the first page we haven't done anything. We have written just the Fourier series expression, and after expanding, what we have seen that the signal is expressed into its multiple frequency component. Okay, so you can see here there is a one DC term and other components are also there. Omega naught is the fundamental frequency term, 2 omega naught, 3 omega naught, they are the multiple frequency term. Okay, and after that we have discussed what Fourier series is exactly doing for us, why this analysis is important for us. Is that clear? Give me a reply. Is that clear? So this is the purpose why we are using Fourier series in power electronics. Is that clear? Now, if you have seen this expression, in this expression we have three coefficients, A naught, An and Bn. These three coefficients are there. Okay, so what are the Fourier series coefficients? So we have three coefficients here. A naught, which is calculated like this, 1 by t. Within the time period t, we will integrate this signal xt, and this is called the average value of signal as well. This is the average value or DC value of the signal. Okay, average value or DC value of signal. Other coefficient that we have is An, and that is 2 by t within the time period t, x of t cos n omega naught t dt. So this is again the Bn, An, and now we will write Bn. So these are the coefficients that we have to calculate, x of t sin n omega naught t. So these three coefficients we need to calculate. Okay, these are called the Fourier series coefficients. So we will calculate these coefficients, and after calculating these coefficients, when we will put their values and expand for further values of n, we will get the complete expression. Okay, and that expression will tell us what frequency components are present in a particular signal. Is that clear? Now the task is we have to calculate these three integral, and solving integral is never an easy task, isn't it? Solving integral is never an easy task, but here we have to solve three integrals, isn't it? Here we have to solve three integrals. So now if you see here, A naught is a constant term. A naught is DC value, and DC value, DC signals are even signal. If you have gone through signal and system, you know DC values, the DC are even signal, if you see an is having cos with it. Cos is also even, isn't it? So a naught is what? A naught is even. This is an is having cos with it, so this is also even, and this is having sine with it, so this might be odd. You know that cos is even and sine is odd, isn't it? So there is even and odd terms coming in the Fourier series. Now if we'll use these particular phenomena here as well, then we will be calculating these coefficients very easily. So there are three coefficients a naught, an and bn, and we will use these integral to solve these. We will use this integral to solve this coefficient, and solving integrals has never been an easy task. Now here we have to solve three integrals. So is there any way so that this calculation we can reduce? Of course there is. So there is a way through which we can reduce the calculation of this integral. Okay, so there are few concepts of symmetry we will use, and we will just further reduce this task of calculating this integral. So the first concept is even symmetry. So if the signal is even symmetrical, means if we are doing x of minus t, still we are getting x of t. Okay, or we can say even signals are symmetrical about y-axis. Okay, like the signals cos waveform. So if you have seen cos waveform, they are symmetrical about y-axis. Square wave like these square wave, if we have a square wave like these are symmetrical about y-axis. So whatever they have on the right side, they have exactly the same nature of signal in the left side as well. So they are even signal. What if the signal is even? So if the signals are evens, you have seen we have three coefficient in this expression. A naught is having even nature, and this coefficient an, which is written with cos, this is also even, but sine is an odd signal. So what you can refer here, if the signal is even signal, definitely bn coefficient will be 0, because sine is an odd signal, isn't it? So sine terms will not be there. So what we can refer from here, if the signal is even symmetrical, we will be calculating a naught, we will be calculating an, but one thing that we are very sure that bn is equals to 0. So do not waste your time in calculating bn. Is that clear? We will calculate a naught and an, and we will not be calculating bn. So do not waste your time in calculating bn. Is that clear? I hope it is. Next thing is odd symmetrical. So if the signal is odd symmetrical, means if we are doing x of minus t, we are getting minus of xt signal, or we can say odd symmetrical signal are anti-symmetrical about y-axis. Odd signals are anti-symmetrical about y-axis. Like, see, if we have a sine wave signal, if I draw a sine wave signal, you can see these signals are anti-symmetrical about y-axis. Whatever they have on the right side, they have the same shape in the left side, but in the opposite direction, isn't it? So they are anti-symmetrical about y-axis. So what if the signal is anti-symmetrical about y-axis, or the signal is odd? So if the signal is odd, a naught and an, they are, a naught is even because it is DC term, and an is written with cos. So it also represents the even symmetry, isn't it? So what will happen? If the signal is odd, why do we calculate the even term? They should not be there. I mean, they must be 0. So if the signal is odd, what will happen? A naught and an both must be 0, and we will only waste our energy in calculating bn. Is that clear? Give me a reply. Is that clear? We are not going to waste our energy in calculating a naught and an, since the signal is odd, and a naught is DC term, it is even, so it might be 0, it will not be there. Okay, very good. And an is having cos with it, so if the signal is odd, no cos term, no even term will be there, so a naught will be 0. We will only be calculating bn, so we will waste our energy in calculating bn only. Okay. Next symmetry is, so see, if the signal is found to be an odd signal, the efforts that we are wasting in calculating this coefficient will reduce like anything, isn't it? We are not calculating A naught and An, we are only calculating Bn here. Is that clear? Now, next thing is also there if the signal is half wave symmetrical. So if the signal is half wave symmetrical, that means x of t, this is equals to minus of x t plus minus t naught by 2. Okay, if the signal is half wave symmetrical, means like this. If the signal is half wave symmetrical, what do we mean by half wave symmetry? See this particular signal. This is t by 2 and let us consider this is t naught. So you can see it is having equal positive and negative half. So if we shift this particular signal by t by 2 and then if we put the minus sign here, we will again be getting the same signal. Or you can understand by looking into the waveform, it is having positive and negative half both equal. Okay, so if it is like that, the signal is found to be half wave symmetrical. Now what will happen if the signal is found to be half wave symmetrical? So if the signal is found to be half wave symmetrical, one thing that is very sure, Fourier series expansion will only have odd harmonics. So Fourier series expression will only have odd harmonics, means it will be only written for n equals to 1, 3, 5, 7, 9 and so on. Okay, it will not be expected that the signal might be having even component. Okay, like n equals to 2, 4, they must be absent. So if the signal is half wave symmetric, Fourier series expansion will contain only odd harmonic component, no even harmonic component will be there. Okay, so what will happen if the signal is both even plus half wave symmetrical? If the signal is both even plus half wave symmetrical, then what will happen? So if the signal is even, then the Fourier series expansion, what coefficient will be calculating? We will be calculating A naught and An. Bn will not be there and Bn has sine term. So if the signal is even plus half wave symmetrical, that means no sine term will be there and only odd cosine term will be there, isn't it? So this is the learning that we have from here. If the signal is even and half wave symmetrical, only odd cosine terms are present. Okay, only odd cosine terms are present. Now let us suppose that signal is odd plus half wave symmetrical. So if the signal is odd plus half wave symmetrical, then what will happen? Since it is half wave symmetrical, so only odd harmonic components will be there. And if it is odd, in that case what will happen? So if it is odd, A naught and An are 0, only Bn is there and Bn is having sine with it, isn't it? Bn is the coefficient of sine term. So only sine terms will be present, but they might be carrying only odd harmonics. So what we can write here, only odd sine terms are present and rest of them will be absent. No cosine term will be there if the signal is odd plus half wave symmetric, and no sine term will be there if the signal is even plus half wave symmetric. Is that clear? Give me a reply. Is that clear? Nikhil, Nayan and everybody there? So through this concepts of symmetry, we can reduce the calculation of these three integrals. Solving integral has never been an easy task and we have to solve three integral here. So if we know the concept of symmetry, we can reduce our calculation very much, isn't it? Is that clear? Very good. So these concepts we have to learn. Okay. Now trigonometric Fourier series of a square wave. Now we are coming to power electronics and we will be focusing more on the Fourier series used in power electronics. So what I have recognized, there are only three types of waveform there in power electronics whom Fourier series expression you should know how to write them, and if you practice to memorize that, it will be very good for you. So in that particular thing, the first case is a square wave. In most of the converter, like if you see in this square wave where you are going to see this, you will see this square wave in rectifiers. You will see this square wave in rectifiers, specifically single phase full wave rectifier. You will see this waveform in choppers as well. Okay, and you will see this waveform in single phase VSI and CSI. Okay, most probably rectifier and single phase VSI CSI, you will see this waveform very coming very rapidly and very frequently, and you have to write the Fourier series expression for this particular waveform. So if we practice how to write the Fourier series expression for a square wave waveform, everything becomes very easy, isn't it? So what we are going to write here, we are going to write the Fourier series expression for a square wave. Now from this particular result, I will let you know, you can conclude that, you will be able to conclude that through this particular expression we can write further expression as well. And there are only 3 types of Fourier series expression that you have to just go through, and you have to remember. Nothing apart from that, nothing you will get in power electronics which is coming out from this particular waveforms. Okay, voltage source inverter and current source inverter NAND. Okay, these are the part of inverters. Okay, now so we have to write the Fourier series expression for this square wave. Now if we see this square wave, so I am going to really erase this particular part. So Fourier series expression for a square wave. Now if you see this square wave, now can you just let me know this is even or odd, or whether this is half wave symmetrical or not? What type of nature this waveform is having? The waveform drawn in front of you, what type of nature this waveform is having? Whether it is even, whether it is odd, or whether it is half wave symmetrical as well. So if you look into this waveform, the positive and negative parts of these waveform are equal, isn't it? So this is half wave symmetrical, this is half wave symmetrical waveform, and this waveform is anti-symmetrical about y-axis. This part and this part are equal but opposite in nature. So this is what? This is odd as well. Okay, so now these two things that you have concluded, that this is half wave symmetrical plus this is an odd signal, these are saying that A naught will be 0, AN will be 0, and we have to calculate only Bn, isn't it? We have to calculate only Bn, and whatever Fourier series expression will be having, it is only defined for odd values of n, isn't it? The values of n might be odd here, and this particular concept we are getting from half wave symmetry. And since the signal is odd, A naught and AN will be 0, we have to calculate only Bn, isn't it? We have to calculate only Bn coefficient. Now, so calculate Bn coefficient for this particular waveform. So how do we calculate Bn? So the expression of Bn is 2 by T for the time period T, x of T sin n omega naught T dt. Okay, now integration variable might be T or might be omega T as well. Here we are taking T, in the next case we will take omega T. So this is not a confusion at all. Okay, now we have to integrate this particular expression. Now we can also write this expression in this particular format. See, we can write this from minus T by 2 to 0. From minus T by 2 to 0, xt is having a value minus A sin n omega naught T dt, and from 0 to T by 2, from 0 to T by 2 it is having a value A sin n omega naught T dt, isn't it? A sin n omega naught T dt. Now we have to integrate this and we will get the required result. Okay. Now how do we integrate this? See, once you will integrate it, what you are going to get here? Let me take A common from here. So let me take A common. So if I take A common from here, and if I integrate sine, integration of sine is what? minus cos. Okay, so minus is already there, so we may write it cos n omega naught t. Since the variable is t, so n omega naught will treated as constant, so it will come here. The limit is minus t by 2 to 0, isn't it? And if we integrate it, we will get minus cos n omega naught t divided by n omega naught, and the limit will be what? Limit will be 0 to t by 2, isn't it? This is what we will get. Now if we put the limit here, okay, is there any doubt till now? I don't think so. Okay, so let me put the limits here. So Bn will be what? Bn will be 2a over t. Now if I put the limits here, see, let me take n omega naught out as well. So if I take n omega naught out as well, okay, only cos will be there, and now it will become easy to put the limit. So if I put the limits here, if I put the limit 0 here, this will be 1, and if I put the limit minus t by 2, this will be 1 minus cos n omega naught t by 2. This will come in the first expression. And what do we have in the second? In the second, we will be having c. So in order to absorb this minus sign, we will put the lower limit first. So again it will be 1 minus cos n omega naught t by 2. Is that correct? Yes, absolutely correct. Now can you tell me what is omega naught t by 2? Omega naught t by 2. So omega naught is 2 pi by t into t by 2. That will give us pi. Okay. So in the next line, if we write it pi, so it is 2a upon t n omega naught 1 minus cos of n pi. Again we have 1 minus cos of n pi here, and in between we have plus sign. So from here what we are getting, 2a upon, see again we have omega naught t here. Okay, so what will be the value of omega naught into t? 2 pi by t into t, that will give us 2 pi. So this will become 2a upon 2 pi, or let it be, we will put it later. Okay, n omega naught. Now from here we are getting 2 minus 2 cos n pi. Okay, 2 minus 2 cos n pi, or we can also write it, let it be omega naught t, that is coming out to be 2 pi. So let me write it 2 pi n, and let me take 2 common from here as well. So it will become 1 minus cos of n pi. Okay, so again what we are getting? Again we are getting, this will become 2a. So Bn will become 2a upon n pi 1 minus cos of n pi. So this is what we are getting as Bn. Now you know one thing, that cos n pi, this is equals to 0 when n is even. Okay, and cos n pi, this is equals to minus 1 when n is odd. Okay, now can you tell me, we have to put the odd values of n here or even values of n here? This is a very well known fact, n omega naught, frequency and time period. What is the relationship between them? Omega naught, if you are expressing omega naught in radians, okay, this is equals to 2 pi by t. If you are expressing in hertz, frequency is 1 by t, time period. Okay, clear, Nayan? Now just follow this particular calculation. Now can you tell me whether we have to take n values odd here or n values even here? Will you please just let me know? We have to consider n values even here or odd. Our signal is half wave symmetrical. If you have seen here, the signal is half wave symmetrical. So n value we have to take odd. Okay, so is there any doubt? Cos n pi is 0 for n equals to even, and we don't have to consider even. Cos n pi is minus 1 when n is odd. Okay, again these are fact, you can check those. Okay, so we have to take odd values of n. So Bn will be what? Bn will be, if I put cos n pi to be minus 1, Bn will be 4a upon n pi. considering n is odd. Okay, so what we have done, we have calculated this coefficient Bn. Okay, we have calculated this coefficient Bn. Now what will be the Fourier series expression? So the Fourier series expression x of t, this is equals to a naught is 0 plus summation n equals to, n values are odd here. Okay, Bn, an coefficient is also 0, Bn sin n omega naught t, and Bn value we have calculated 4a upon n pi sin of n omega naught t. Okay, so this will be the Fourier series expression of a square waveform. This will be the Fourier series expression for a square waveform. Now, is that clear? Is there any doubt? How we have calculated? Is there any doubt? Give me a reply. Okay, very good. This is so simple. This waveform is half wave symmetrical and this waveform is odd. So it is odd. So one thing is clear, a naught is 0, an is 0. Only Bn we have to calculate, and since it is half wave symmetrical, so it is defined that n value might be odd only. Okay, no even values will be there. Now Bn we have to calculate, so we have used the Bn formula, and xt value we have written here. So from minus t by 2 to 0 we have written minus a, from 0 to t by 2 we have written a. Now we have to integrate and put the limits, and finally if we adjust it, we will get this expression. Okay, if we adjust this, we get this particular expression. So xt is coming what? 4a upon n pi sin n omega naught t. So guys, if we have this particular square wave waveform, now can you tell me what is the Fourier series expression for this waveform? This particular Fourier series expression for this waveform will be Vt equals to summation, the values must be odd only, n equals to 135 to infinite 4a upon n pi sin n omega naught t. So this is the expression of this square wave waveform. Now you will see these kind of square wave in inverters, you will see these kind of square wave in rectifiers as well. In some cases of rectifiers you will see this kind of waveform as well. So how to write the Fourier series, we are just going to discuss. Now please let me know, did you get how to write the Fourier series for a square wave? Just let me know. For a square wave, it is 4, whatever is the amplitude of signal, 4a upon n pi sin n omega naught t. Okay. Now you will get a question in exam, and this might be related to inverter or rectifier. One waveform will be given to you, and it might be what will be the fifth harmonic component, what will be the fundamental component of seventh harmonic component, what will be the RMS value of third harmonic component. So for that, if you recognize, if you remember this particular expression, suppose you have to calculate the third harmonic component, you have to put the values of n to be 3 only. Okay, so this is how we have solved this particular problem. Now from here we will be deriving n number of results. Okay, so this is the first case that you have seen. Now come to the second case. Now in so many cases like semi converter, okay, or full wave rectifier, you may even get this particular kind of waveform as well. Now what is the difference between these two waveforms? If you see, the difference is this waveform is shifted towards left side by an angle phi. This waveform is shifted towards the right side by an angle phi, isn't it? By an angle phi. So is there any change in the Fourier series waveform? Now see what will be the Fourier series waveform for this particular waveform. So it will be summation n equals to 135 to infinite. There will not be any change in the coefficient part, okay, 4a upon n pi. But if you see, this waveform is right shifted, isn't it? Now what will happen if suppose this signal is Vt, let me call this V dash t. So what will be V dash t? V dash t is simply V of t minus phi, isn't it? If this would have been shifted towards left, it would be Vt plus phi, isn't it? So this waveform is a shifted version of it. It is shifted by an angle phi. So what will be the change in the expression? No change will be there in this particular part, but this waveform is only shifted by an angle phi. Okay. Now whether it is positive or negative, that depends upon the shifting. Now this will be the expression for this waveform. Now this will be the expression for this waveform. Now give me a reply. Is it clear to you? Give me a reply. Is it clear to you? This is the first case you will get in power electronics. In most of the cases you will see this waveform. In some of the cases like semi converter you will see this waveform, and there is third example as well. Apart from these three, nothing else you will see in power electronics, and that's why I am very sure after completion of this lecture, Fourier series in power electronics will become a very easy topic for you. You will be able to write the expression as easily as possible. Is that clear? Any doubt till now? So these two cases we have discussed. The third case that you will see is this particular waveform, and this particular waveform is called as quasi square wave. Okay, the name of this waveform is quasi square wave. Where will you see this particular waveform? You will see this particular waveform in inverters. Okay, in inverters, specifically PWM inverters or three-phase inverters, you will see this waveform. You will also see this waveform in single phase and three-phase rectifiers. So in these two chapters you will see this kind of waveform, quasi square wave. Okay, so these kinds of waveforms are called as quasi square wave. So what is there? If you see, this waveform is starting here from theta angle, and for one particular half cycle it is expanding only from theta to pi minus theta. Okay, for this particular duration, and in the next half cycle it is expanding from pi plus theta to 2 pi minus theta. Okay, same duration, the same duration, whatever is the duration here, the same duration is there as well. Now if you see this waveform, what you will recognize, see, I think this is drawn wrongly. This part should be here, okay, and this part should come here like this. Okay, this is not correct. So this waveform is what? This waveform is odd, plus this waveform is odd, plus this is half wave symmetrical as well. So again the things will be A naught will be 0, An will be 0, and we will calculate only Bn. Okay, Bn will be there, and n values will be odd here. N values will be odd here. Okay, let me do one thing. Let me use blue color for this, so this might be erased. Let it be. Okay, so this waveform is not properly drawn on the left hand side. Okay, this is not correct. This should be the correct form of waveform. Okay, again this will not be there, this will be there. Okay, so this waveform is odd plus half wave symmetrical. Okay, odd plus half wave symmetrical. What you can do, you can just ignore the left hand side part. Okay, so this waveform is also odd and half wave symmetrical. Again, A naught is 0, An is 0, Bn will be there. Okay, Bn will be there. N values might be odd here as well because half wave symmetry is there. So we have to calculate Bn again as well. So how do we calculate Bn? Again, if we want to calculate Bn, same formula we will use. Bn is 2 by T for the time period T. This is x of T sine of n omega naught T, and now let us consider that I am taking the variable as d of omega naught T. Okay, before that I have taken the variable T. Sometimes you may also get confused with taking variables. So here I am taking omega naught T. Okay, because this is not a problem at all. So you will stop thinking about this particular thing. Now what is the time period here? Time period here is 2 pi, isn't it? The time period here is 2 pi. So 2 or let us write this letter. Okay, now what we can do here, we can express this waveform. If you see, for one particular time period, this waveform has two portions. From theta to pi minus theta, this is having a part A. Its value is A here, A sin n omega naught t and d omega naught t. And for this portion from pi plus theta to 2 pi minus theta, it is having negative value minus A sin n omega naught t d omega naught t. Okay. So now we have to integrate these two portions and we will get the required answer here. So again, what I am doing here, I am taking I am taking A outside. So if I take A outside and then if I integrate it, we will get minus of cos n omega naught t, and now our variable is omega naught t. So omega naught t is variable, so we will get only n here, okay? And the limits are theta to pi minus theta. Now when we will integrate this particular part, what we are going to get, now this minus get resolved inside, we will get cos n omega naught t divided by n, and the limits will be pi plus theta to 2 pi minus theta. So we have integrated till this point. साहिल वेकरिया, सर मेरा 2023 गेट में 42 स्कोर आया है, आपसे 3 सब्जेक्ट पढ़े थे, PPS एंड SS, अहमदाबाद से 3 सब्जेक्ट आपसे पढ़े थे. वेरी गुड साहिल. those 3 subjects have helped you scoring 42 marks. Okay, very good. And I am sure if you have given exam from electrical, you have got a very good rank as well, isn't it? So try to give GATE in 2024 as well. If you have done really well in 2023, you have scored 42 marks, I am very sure in the year 2024 you may get a rank under 100 as well. Okay Sahil, very good, very good, very good. So are you following our fundamental series? It will really help you in getting in doing better. Yes, very good, very good. In better in power electronics. Okay, so we have calculated till now. Now what will be the next part? Just put the limits here. So I am taking n outside. Okay, in the next step I am taking n outside. This will be 2a upon nt. Now n we have taken outside. Now we have to put this limit. So minus is there, so I am putting lower limit first. So this will be cos n theta minus cos n pi minus theta. This is what we are getting in first integral, and in the second we have 2 pi minus theta plus pi by. So what we will be getting here? We will be getting cos n 2 pi minus theta and minus cos n pi plus theta. Okay, this is what we have obtained here. सर मेरा सिलेबस कंप्लीट है IMS से, अब सिर्फ मॉक टेस्ट की प्रैक्टिस कर रहा हूँ. वेरी गुड साहिल. So keep on practicing those mock tests, keep on watching those lectures and keep on following our YouTube series as well. Okay, so here we are coming with such initiative that will not only work well for a beginner, the person like you who have already experienced the gate, those will help you in performing better in the upcoming gate as well. Okay Sahil. So now we have this particular thing. Now do you know that cos, let me tell you one thing, cos n theta or cos 2 pi n minus theta, okay, cos 2 pi n minus n theta, they are equal to each other. Similarly, cos n pi minus n theta, this is equals to cos n pi plus n theta. Okay, cos n theta is equals to cos 2 pi n minus n theta. Very good Sahil. Cos n pi minus theta and cos n pi plus theta, they are exactly equal to each other. Now if we put these two values here, we will get 2a upon nt. So cos n theta and this will get added, so it will become 2 cos n theta, again they are equal, so they will also get added, and we can write 2 cos n pi minus n theta here. Okay, so this is what we have obtained here. Now can we put the value of t here? So if we put the value of t, which is 2 pi, we will get this result. Let me take 2 common as well, then this will become cos n theta minus, now if we expand this, we will get cos of n pi cos of n theta plus sine of n pi sine of n theta. Okay, and you know that sine of n pi, this is equals to 0. So what we are getting from here, is we will get 2a upon n pi cos n theta 1 minus cos n pi. So this is what we have obtained here. Okay, 2a upon n pi cos n theta 1 minus cos n pi. Okay, now again we have to take the odd values of n. Okay, you know this concept, cos n pi, this is equals to what? This is equals to plus 1 if n is even. Okay, and this is equals to what? Cos n pi, this is equals to minus of 1 if n is odd. So if even values you will take, bn will come out to be 0, isn't it? And even we can't take because half wave symmetry is there. So we will take odd values, and cos n pi is minus 1. So if we put that value, this will give us what? This will give us bn is equals to what? Minus 1 if you will put, that will become 2. So it will become 4a upon n pi cos of n theta. Okay, so earlier for a full square wave, what we have obtained? Only 4a upon n pi. If you have remember, we have only got 4a upon n pi, but this time we are getting an extra cos n theta in quasi square waveform. Okay, so now if I write the expression here, bn that we have calculated is what? Bn that we have calculated here is 4a upon n pi cos of n theta. So now what will be the Fourier series expression? Fourier series expression for this signal Vt will become, for a quasi square wave, it will be summation n values are odd because half wave symmetrical signal is there. Bn sin n omega t, bn value is 4a upon n pi, 4a upon n pi cos n theta and sin n omega naught t. So this will be the expression. Okay, this will be the expression. This is what we have obtained here. So if we compare here for a square wave, what do we have? So for a square wave we have this expression v of t, this is equals to summation n equals to 135 to infinite 4a upon n pi sin n omega naught t. Okay, now if suppose we have quasi square wave, so for quasi square wave, what do we have? We have this expression v of t, this is equals to summation n equals to 135 to infinite 4a upon n pi, and one extra cos n theta term is there and rest remains same. Now how difficult it is to remember? Tell me. If we have a perfect square wave, the expression is 4a upon n pi sin n omega naught t. If we have a quasi square wave, an extra cos n theta term will be there, isn't it? So first case is perfect square wave. Then if it is a shifted one, you will shift it by plus or minus, whatever is the shifting angle. Then if suppose we have quasi square wave, then in case of quasi square wave, an extra cos n theta term will be there. Nothing else we have to do. Is that clear, guys? I hope this is very, very clear to you. Okay, so this extra term cos n theta is coming, and what is theta here? If we just look into this particular quasi square waveform, this is the theta that we have to put. Okay, this is the theta that we have to put. So these are the only 3 cases. Very frequently these 3 cases you will see in power electronics, none other case will be there. Okay, so if you are able to just calculate the Fourier series expression for these 3 cases, and if you will practice enough, you will be able to memorize these 3 expressions. Okay, ultimately these are only 2. In one we have 4a upon n pi. In the second case, quasi square wave, we have 4a upon n pi cos n theta. So only these two expressions you have to remember, and rest if you'll see now just after this lecture, if you have already covered power electronics, just go to every converter and see whether you are able to write the complete Fourier series expression for that converter or not. I am sure you will be able to. Okay. So this is what we have covered here. Now there is one special case here. Now for this particular quasi square waveform, what is the Fourier series expression? For this particular quasi square waveform, the Fourier series expression is summation n equals to 135 and so on to infinite 4a upon n pi sin n omega naught t. Cos n theta is missing. Okay, cos n theta sin n omega naught t. This is the Fourier series expression for this particular quasi square wave. Okay, now one special case is there, and what is that special case? Let us consider the width of this particular wave pulse is 2d. Okay, the width of this particular pulse is 2d, and let this point is pi by 2. So this distance is d, again this distance is also d. Okay, now this case you will see in PWM case. Okay, in PWM inverter you will see this case, and this is very important as far as the gate exam is concerned. This is very important. This particular case you will see getting repeated every time. Okay, so the width is 2d, this particular distance is pi by 2, and this is d. So what will be the value of theta here? So theta, we can also write that theta is pi by 2 minus d, isn't it? Theta will be pi by 2 minus d. Now if we put the value of theta here, then what we will get? Now if we put the value of theta here, the Vt expression will be summation n equals to 135 to infinite 4a upon n pi cos n pi by 2 minus d sin n omega naught t. Okay, now if you see cos n pi by 2 minus nd, if we expand this expression, what we are going to get? Cos n pi by 2 cos nd plus sin n pi by 2 sin nd. Now cos n pi by 2, you know, this is equals to 0. So what we will get? We will get sin n pi by 2 and sin nd. So this expression will now become Vt is equals to summation n equals to 135 to infinite 4a upon n pi, 4a upon n pi. In place of cos n pi minus d, we will get this particular thing, sin n pi by 2 sin nd and sin n omega naught t. So see, this expression we have obtained for PWM inverter. Very frequently this expression is used in PWM inverter, and you have calculated this without specifically putting any effort, isn't it? Without specifically putting any effort, we have just calculated this expression. So if you are not able to memorize this expression, I am sure you will be able to learn this particular fundamental. Now here you know that theta I have to put pi by 2 minus d, just put it and you will get the expression. And just go through the previous year paper, you will see a lot of time there will not be any gate paper where question from this particular expression is missing. Very rarely it will be there. Okay, so this is very important, and you have calculated this expression without putting any efforts. Okay, so this is what we have learned here. Now what I was saying is there are only 3 expressions, nothing else. So now see this particular waveform, and we have to write Fourier series expression for this particular waveform. Now through the help of what we have learnt in this particular class right now, with the help of that content, we will write the Fourier series expression for this waveform very easily. How? I am very sure about this. See, this waveform you will see in three-phase VSI, okay, in three-phase VSI, three-phase voltage source inverter, 180 degree or 120 degree, you will see this waveform, okay. Now, how we are going to write the Fourier series expression for this waveform? Just see it. So, if we see this particular waveform, we can write this waveform in two parts. In the first case, the waveform is like this. In the first case, we have the waveform like this. Just see. In the first case, we have a waveform whose magnitude is A, this duration is pi, this duration is 2 pi, isn't it? This is the first case. Let me call this V1t. Now, what is the Fourier series expression for this waveform? This is a perfect square wave, isn't it? So, for a perfect square wave, what is the Fourier series expression? The Fourier series expression for V1t will be summation n equals to 135 to infinite 4a upon n pi sine n omega t, isn't it? This will be the Fourier series expression. This will be the Fourier series expression for this square wave part. Now, the next part of this waveform, which we will call V2t. So, if you see V2t, how the V2t is going to look like? See, this is V2t. So, V2t we have from pi by 3 to 2 pi by 3 one waveform. This is pi, this is pi by 3, this is 2 pi by 3, and we have the next part of waveform like this, isn't it? Where this moment is 2 pi. Now, again, what will be the magnitude? It is ranging from A to 2A, that is the magnitude will be A. Now, what type of waveform is this? This is a perfect quasi square wave waveform. So, for this quasi square waveform, what is the value of theta? It is pi by 3. So, what will be the expression for V2? So, V2 expression will be summation n equals to 135 to infinite 4a upon n pi cos n theta, means cos n pi by 3 sine n omega t. See, we have written the Fourier series expression for this waveform. So, this is a square wave, this is a quasi square wave. Now, this waveform is a combination of these two. So, what will be the expression for Vt? So, the expression for Vt will be V1t plus V2t. So, if you are going to add both these expression, you are going to get this particular expression, n equals to 135 to infinite 4a upon n pi 1 plus cos n pi by 3 sine n omega t. So, that will be the Fourier series expression for this waveform, isn't it? So, see, whatever concept we have learned, they are actually very useful for us, and we are able to write the waveforms here, isn't it? So, what will be the complete expression for this waveform? So, the complete expression for this waveform will be n equals to 1, 3, 5 to infinite 4a upon n pi 1 plus cos n pi by 3 sine n omega t. That is the Fourier series expression, isn't it? Now, one thing I would like to tell you about cos n pi by 3. So, about cos n pi by 3, okay, this will be having a value equals to -1 if the n is multiple of 3, like 3, 9 and so on, okay. So, if n is having 3 or 9 or 15 like that value, then cos n pi by 3 will be having a value -1. So, when you will put -1 here, that will come out to be 0, isn't it? So, if it will come out to be 0, what you can write here, that this Fourier series expression is particularly valid for n is equals to 6k plus minus 1, okay. So, writing this limit here is not a good thing. Limit will be n equals to 6k plus minus 1, where k is exactly from 0, 1, 2. So, if we will put like that, n is equals to 6k plus minus 1. If you will put value of k to be 0, you will get 1. If you will put the value of k to be 1, you will get either 6 plus 1, that is 7, or 6 minus 1 will be 5. So, 1, 5, 7 like these you will be getting here, okay. 1, 5, 7, 11, 13 like this you will be getting. So this expression is valid only for n values like 6k plus 1. So even harmonics and all triplen harmonics are absent. Now just go to the previous year gate questions and see there in three-phase inverter. In three-phase inverter cases, they have directly asked this question: which harmonics will be present? So neither the even harmonics will be there, nor the triplen harmonics will be there. Only one, and after one we have fifth, 7th, 11th, 13th harmonic present, isn't it? So there was a one question directly on this particular thing, and there was an indirect question: if the fundamental frequency is 58, what will be the frequency of next harmonic component? So many students have written 150, and that was a wrong answer. Okay, so the next component will be what? 250. Is that clear? Now apart from these three cases, if you see any other case, just let me know. Okay, just get me know about that particular expression. So if you are able to particularly write these expression, you have done everything. Okay, you really just after this class just go and write the Fourier series expressions of the voltage and current waveform of all the converter, and what you will see, you have done wonders. Okay, you will be able to write all the Fourier series expression for voltage and current in every converter. How? See, this is the gate question. Now just read this question: a single phase inverter. You haven't read inverter right now, isn't it? But we are solving a gate question related to inverter with the help of whatever we have covered in this class. So we haven't gone through the inverter, and still we will be able to solve the question related to inverter having 2 marks attached with it. Okay, so that is why today's class was very important. With the help of this class, without even going into the proper topics like inverter, rectifiers or chopper, you will be able to solve gate problem. How? Just see here. So this question is related to inverter, and we will solve this question here without even knowing the inverters. What has been said in this question is: a single phase inverter is operated in PWM mode, generating single pulse of width 2D in the center of each half cycle as shown in the figure. It is found that the output voltage is free from fifth harmonic for a pulse width of 144. So this is the pulse width 2D, isn't it? So 2D pulse width is given to us, which is 144. So what will be the value of D? This will be 72 degree. Okay, this what we can calculate very easily from here. What will be percentage of third harmonic present in the output voltage with respect to the fundamental? Okay, so we have to calculate the ratio of V0 third to V0 1. Okay, now in this particular case, what is the Fourier series expression? This is a quasi square waveform. So in this particular case, we have Fourier series expression like this. Okay, so Vt will be equals to what? Vt will be equals to summation n equals to 135 to infinite 4V upon, here V is there, cos n theta and sin n omega t, isn't it? Now if we put theta is this value, so if we put theta to be pi by 2 minus d, isn't it? What expression we are ultimately getting? We are getting an expression like this: n equals to 6k plus minus 1. Not for that, n equals to 135 will be there. That is for letter case, the waveform that we have done in the last case. So n equals to 135 to infinite. If we put theta to be pi by 2 minus d, what we are going to get? 4V upon n pi sin n pi by 2 sin n d and sin n omega t. Okay, so what we have to calculate here? V0 1. So what will be the value of V0 3 and V0 1? So V0 3 means n value we have to put 3 here. So if we put the value of n to be 3, we will get 4V upon 3 pi sin 3 pi by 2 will be 1. So just ignore that. Sin 3 pi by 2 will be 1. So just ignore that. And sin 3d. So this will be the third component. What will be the fundamental component? We will put the value of n to be 1 here. Okay, so 4V upon pi sin d. Now we have to calculate what will be V0 3 upon V0 1. So once you will divide, you will get sin 3D upon 3 sine D. Now just put the value of D. So it will be 3 into 72 degree divided by 3 into sine 72, and what you will get? You will get 19.6% here. Okay, so this option number 3 is correct. This question contains 2 marks and you haven't spent 2 minutes in this question and you don't know the concept of inverter. Okay, so without actually knowing the proper concepts of inverter, through the concepts of Fourier series required for power electronics, we have solved this question, isn't it? We have solved this particular question. So this is the beauty of this foundation course. Okay, this is what students are getting from this foundation course. So if you have done these courses, if you have followed these lectures, I am very sure you are going to rock in power electronics. You will be able to do wonders in power electronics. Okay, so this is not just one question. Let me give you another question as well. See this particular question. The waveform of the current drawn by semi-converter. Semi-converter means rectifiers, isn't it? So this question is related to what? This question is related to rectifier. Now have we covered rectifier in the class? Not at all. So without covering the rectifiers, we will be able to solve this question. How? Just see. So the waveform of the current drawn by semi-converter from a sinusoidal AC voltage source is shown in the figure. I value is given 20. Okay, let me use red color. So I value here is what? I value here is 20. So here we are given that I value is 20 ampere. The RMS value of fundamental component of current will be what? We have to calculate the RMS value of fundamental component. Means we have to calculate the first component and we have to calculate its RMS value. Okay. Now this question is related to rectifier. Now without going into the rectifier, we will be able to solve this question. How? Just see. This waveform is quite similar to the quasi square waveform, but quasi square waveform does not end at 180, isn't it? This ends before 180. So if suppose we shift this waveform by an angle 15 degree like this, if we just shift this waveform by an angle 15 degree, okay, so if this angle become 15 and if this angle become 165, this will become a proper quasi square waveform, isn't it? This will become a quasi square waveform, isn't it? So now this is a quasi square waveform whose theta value is how much? Whose theta value is now 15 degree, isn't it? Before that it was not a quasi square waveform. If you see quasi square waveform, it just end before theta, before pi, isn't it? Before 180 it ends, and this duration is equals to this duration. So that was not a perfect quasi square waveform. We have to make it a perfect quasi square waveform, and for that if we shift it by 15 degree angle, it will become a quasi square waveform. Because now if you see this duration, okay, this duration is exactly equals to this duration. So it has now become a perfect quasi square waveform whose theta angle is 15 degree, and we have shifted this waveform towards left. So whatever is the expression for quasi square waveform, we have to add plus 15 because we have shifted it by 15 angle, isn't it? So now what we are going to do, see, earlier what is the expression for quasi square waveform? The quasi square waveform expression is 135 to infinite 4a upon n pi cos of n theta sine of n omega naught t or omega t. This is for perfect quasi square waveform. But in our case, what is the thing here? N equals to 135 to infinite 4. In place of a we have I here, 4a upon n pi cos of n, theta value now becomes 15, cos of n into 15 sine of n, and it will be omega naught t. What we have done, we have shifted our waveform 15 degree towards the left. So what we will do, we will add that particular duration which we have shifted here, nothing else. And that is the purpose why I have just made you aware of what happens if we shift the waveform, how it is going to affect the Fourier series expression. So that shifted amount will be there only, isn't it? But we don't have to do anything for that. If you practice enough, you will get to know that. We have to calculate the fundamental RMS component. Okay, so if this is the I naught, what will be the fundamental component and its RMS value? So see, for fundamental RMS component, n value will be what? 1. Okay, 4i upon n is 1, and we have to divide it by root 2 in order to calculate the RMS value. If you have to calculate the maximum value, we don't divide by root 2, okay, or fundamental value. Cos n value will be 1 and 15 will be there. So this is what we have calculated. After you calculation, you will get 17.4 ampere. Okay, after the calculation you will get this value. So see how easily we have solved this question without even going into the proper concepts of rectifier. 1, 2 and 3 line, and that's it, isn't it? So right after this class, just go and see if you are able to write the Fourier series expression for all the voltage and current waveform for different converter, and not only that, you are solving gate questions as well, isn't it? See the next question, and this question was the latest question, 2018, having 2 marks. Now see this question, an inverter has a periodic output waveform. Again, inverter is there and we haven't covered inverter yet. Has a periodic output voltage with the output waveform as shown in the figure. So this is what? This is a quasi square waveform. This is a quasi square waveform. Okay, and in case of inverter, you know that theta value needs to be put pi by 2 minus d, and through that you can have just the particular expression. Now this pulse width is 120. So pulse width is alpha. We will write pulse width to be 2d, which is given 120. So d value will be 60 degree. The RMS fundamental component of the output voltage will be what? Okay, so this is what we have to calculate here. So in that case, now since you have become aware of this particular thing, I am able to write the expression directly. So what will happen here? The expression is 4v upon n pi summation n equals to 135 to infinite sin n pi by 2. Okay, in case of PWM inverter, this is the waveform and this is the expression sin n omega t, isn't it? What we have to calculate? The RMS fundamental component. So if this is the expression for V naught, RMS fundamental component will be what? For that n value will be 1, and this is 4 into what is the value of V? V value here is 1. So we will put 1 here upon n value will be 1. We will divide by root 2 pi. Sin pi by 2 will be 1. Sin n value is 1 and d value is 60 degree. Okay, d value is 60 degree. So once you will calculate it, you will get answer as 0.78 volt. See, 1, 2 and 3 line, and that's it. Okay, no fourth line is required. This is how you can solve this question, and you can easily obtain 2 marks. Whether we have covered this in our class? Yes, of course we have. See this special case we have done. See, this is related to this special case, isn't it? So this is how you can solve gate questions very easily. Okay, now see this particular question. The same question is there but differently asked. Inverter has a periodic output waveform. Same waveform is there, quasi square wave. With reference to the output waveform given in the figure, the output of the converter will be phi from fifth harmonic when what will be the value of alpha. Okay, so see again I am writing the expression. V naught expression is summation n equals to 135 to infinite 4 v upon n pi sin n pi by 2 sin nd and sin n omega t. Now what we are saying that fifth harmonic component is 0. Fifth harmonic component is 0, that means 4v upon n pi sin n pi by 2 sin nd. Okay, for n equals to 5. Okay, so if we put n equals to 5 here, fifth harmonic component means 4V upon 5 pi sine 5 pi by 2 sine 5D, this is equals to 0, or we can say sine 5D is equals to 0, or we can say that 5D is equals to 0, or we can say D 0 pi 2 pi like that, or D will be equals to what? D will be equals to pi by 5, 2 pi by 5, 4 pi by 5 like that, isn't it? Now how much is pi by 5? 360 by 5 is how much? 360 by 5 is 72 degree. Okay. How much is 2 pi by 5? This will be 144. 4 pi by 5, this is 288, isn't it? Isn't it? Now what will be the value? Pulse width. We have to calculate the pulse width, isn't it? The output with respect to the output waveform given in the figure, the output of the converter will be from the value of alpha, means we have to calculate 2D, isn't it? So if the D value is 72, 144, 288, what will be the value of 2D? What will be the value of 2D? I think this calculation that we have done is wrong, okay? Pi by 5. Pi by 5 is how much? 360 by 5. 360 by 5 is 360 by 5. 72. It is 72. Okay, it is 72. This is 72. This is 144. Okay, and we can ignore these values. So what will be the value of 2D here? Is there any wrong calculation that we have done here? V naught fifth will be 0, so sine 5D will be 0. So 5D will be, D will be pi by 5. D will be pi by 5 and 2 pi by 5, 4 pi by 5. So 2D will become what? 2D will become 144, but it is not there in the option. So I think I have missed one option here, isn't it? Nayan, 180 by 5. Oh, that mistake. Yes. Pi by 5 is actually 36 degree. Okay, it is 180 by 5, not 360 by 5. If we are doing 360 by 5, then it will come 72 degree. Okay, so this is 36 and this will be 72 and this will be 144. So if we have to calculate the pulse width, that is alpha. Now alpha is exactly equals to what? Alpha is 2D. Okay, so with 36, 2D will be become 72. With alpha equals to 2D, if we take D value to be 72, it will become 144. If we take the value of D to be 144, then it will become 288, and 2D can never become more than pi. It will not be greater than pi. So it is getting more than pi. Okay, so we will ignore this value. This shall not be there. So answer might be 72 or 144. Now you have to see whether 72 is given here or 144 is given. So 72 is given, isn't it? 72 is given, so this is the correct answer. Okay, pi by 5 it is 36, not it is 72. What I have mistaken, pi by 5, instead of 180 upon 5 I have calculated 360 upon 5, so that is wrong. Okay, pi by 5 is 36 degree, 2 by 5 is 72 degree, 4 pi by 5 is 144. But we have to calculate alpha, which is exactly equals to 2D, the pulse width. So it will become 72, 144 and 288. 288 we can't take because 2D can never be greater than pi, isn't it? Will it be? See, this is the pi na. So 2D, this pulse width can never become greater than this length pi. Now here it is getting over pi. So this we can't accept. So answer is 72 or 144. Now since it is MCQ, only 72 is given, so this is the correct answer. Now it may be, if there is no option, then which should be taken, 72 or 144. See, if it is an MSQ answer, either they might give 72 or 144, as they have given 72 as answer here. If this is an MSQ, question, they might give both the answer. Okay, they might give both the answer. In that case, both will be correct. If you have chosen only one, that will be a wrong answer. Okay, so this type of question may come in your MSQ category as well. If I want to make it MSQ, I will change one option with 144. Now both the options will be correct. Okay, is that clear, Nayan? So this is all about today's lecture. Okay, just go and watch this lecture again and again, and we have covered a very important concept here, how to write the Fourier series expression for different converter, and only 3 cases we have discussed. Now only through these 3 cases you will be able to write the Fourier series expression for all the voltage and current waveform in all the converter. Nothing else will be required. Okay, just go and write the expression, just see the expression. If you are not able to write, just see the expression. You will see every expression is written with the help of these analysis. And not only that, you are able to solve the gate questions as well. So this is all about today's lecture. Now we have almost completed 3 lectures in this foundation series, and all these 3 lectures are helping students very well. Okay, now in the next lecture, lecture number 4, we will be covering the concepts of RMS value, how to write the RMS value of different converters, waveforms. Okay, and specifically we will be talking about the cases that we are getting in power electronics, how to calculate the energy and power in different cases, like when both voltage and current are sinusoidal. If suppose voltage is sinusoidal but the current is not sinusoidal, if the current is sinusoidal but voltage is not sinusoidal, in that case how do we calculate the power for different converters? Okay, so this will be the topic for the next lecture. This is all about today's lecture. I hope this will serve its purpose. This lecture has served its purpose, and now you are able to get this concept of writing Fourier series for different converters very easily. Okay, so thank you so much, and you can see the strip running on the screen. If you feel interested, you can call on this number. Just go to the description box. You can join our Telegram channel, and you can also join our zero fee program to have the flavor of our courses, our content that we are offering. So thank you so much.